In January 1942, Boeing Plant 2 in Seattle was meant to churn out flying fortresses fast enough to darken German skies, but the factory resembled an industrial traffic jam instead. 63 B-17 bombers sat incomplete on the assembly line, each one a promise America had yet to fulfill. The Army Air Forces had ordered 3,615 bombers for the year, yet Boeing had delivered only 9. General Henry Hap Arnold, commanding the Army Air Forces, wasn't merely disappointed, he was furious. At a tense January 15 meeting with Boeing executives, he made it abundantly clear, without bombers, there could be no strategic bombing campaign, and without such a campaign, American soldiers would face the Nazi war machine entrenched for years. The math was grim but simple. The bottleneck wasn't manpower. Boeing had hired over 30,000 workers in 6 months, many women who had never set foot in a factory. Nor was it materials, aluminum flowed in faster than it could be used. The issue was something unexpected, the bombers themselves were too complex to build quickly. Each B-17G required 140,000 parts, and the wings alone demanded 12,000 rivets per side to attach 7 overlapping layers of aluminum to a framework capable of withstanding up to 6 gs in combat. Traditional assembly techniques, perfected on smaller aircraft, collapsed under the B-17's complexity. Production manager Philip Johnson patrolled the factory floor at 5 a.m., clipboard in hand, observing the same chaos daily. At Wing Assembly Station 4, 17 workers crowded a single wing section, constantly in each other's way. One finished a seam, only for another to need the same spot, and then a third to follow. Johnson timed the process, 20 hours and 14 minutes to complete a wing. The British were losing bombers faster than that. Every unchallenged Luftwaffe fighter meant more ships sunk in the Atlantic, more factories running in Germany, and more time for the Nazis to consolidate Europe. Boeing's engineers had tried everything, retooling access points, designing specialized jigs, adjusting crew sizes, but nothing worked. The blueprint's rivet pattern forced workers into overlapping sequences that could not be parallelized. By late January, executives whispered to the Army that targets might not be met, even considering handing production to Douglas or Consolidated. A classified memo on January 28, titled Crisis Assessment B-17 Program Viability, reflected the stakes. Wing Assembly Station 4 looked like organized chaos that wasn't. A massive aluminum skeleton lay on a jig, with 7 precisely drilled sheets waiting to be riveted in order, starting at the wing root and marching to the tip. Rivets had to follow rows parallel to the leading edge, reinforcing each other like shingles, a structurally perfect plan on paper but a nightmare on the floor. Each rivet required a riveter above and a bucker below to press the molten aluminum into place, perfectly timed or risk a loose rivet that wasted minutes. Row 2's crew waited for Row 1, Row 3 for Row 2, as inspections slowed progress. Pneumatic guns rattled entire bodies, hoses tangled, and workers navigated a cramped, heated space where aluminum expansion misaligned pre-drilled holes. Frank Szymanski, 31, a former Chrysler worker, joined the swing shift at Wing Assembly Station 4 with his wife and daughters in tow. Unlike other riveters, he didn't just focus on a single rivet, he watched the entire process, noticing how delays cascaded across the wing. On February 4, while on break, he studied a completed wing section and recalled Chrysler door panels, assembled from 4 corners inward to allow parallel work. He sketched a new pattern on the back of his time card, clustering rivets around accessible ribs and following the wing's contours. It looked chaotic, but it allowed multiple workers to rivet simultaneously without overlap. Structurally, it seemed feasible, as failures usually occurred at transitions, not within rows. Frank knew his idea would likely be dismissed, but he had one advantage. Swing shift supervisor Bill Hendricks, a former sheet metal worker, listened to floor workers, a rare opportunity for innovation in a rigid hierarchy. On February 11, Frank caught Hendricks during the 8 p.m. shift change and showed him his sketch. Hendricks studied it carefully, then said something Frank hadn't expected: "This violates every structural loading principle Boeing uses." "You know that, right?" Frank nodded, aware, or at least suspecting, the risks. Hendricks continued, explaining that the parallel rivet pattern wasn't arbitrary, it followed predictable stress lines along the wing, ensuring fasteners were densest where stress was highest, a principle rooted in Theodore von Karman's work at Caltech in the 1920s. A fully loaded B-17 wing experienced enormous bending stress in flight, and the parallel pattern perfectly distributed these forces. Frank's clusters, dense around structural ribs and following access convenience rather than stress lines, seemed gibberish from an engineering perspective. Under sustained combat, microfractures could propagate and the wing could fail, endangering lives. Hendricks shouted over pneumatic guns, acknowledging these risks, then asked a question that changed everything: had von Karman considered assembly efficiency? Frank looked confused. Hendricks explained that while theoretically weaker, Frank's pattern could produce practically stronger wings by reducing errors caused by exhaustion, cramped positions, and fatigue. This was heresy. Boeing's hierarchy assumed procedures dictated quality, not worker reality, but Hendricks had seen firsthand how theory and practice diverged. Exhausted riveters missed rivets, inspectors approved marginal work, productivity stalled. Could Frank's pattern, by minimizing overlap and fatigue, actually yield more reliable results? Hendricks folded the sketch, promising to speak to someone. Row 2's crew waited for Row 1, Row 3 for Row 2, as inspections slowed progress. Pneumatic guns rattled entire bodies, hoses tangled, and workers navigated a cramped, heated space where aluminum expansion misaligned pre-drilled holes. Frank Szymanski, 31, a former Chrysler worker, joined the swing shift at Wing Assembly Station 4 with his wife and daughters in tow. Unlike other riveters, he didn't just focus on a single rivet, he watched the entire process, noticing how delays cascaded across the wing. On February 4, while on break, he studied a completed wing section and recalled Chrysler door panels, assembled from 4 corners inward to allow parallel work. He sketched a new pattern on the back of his time card, clustering rivets around accessible ribs and following the wing's contours. It looked chaotic, but it allowed multiple workers to rivet simultaneously without overlap. Structurally, it seemed feasible, as failures usually occurred at transitions, not within rows. Frank knew his idea would likely be dismissed, but he had one advantage: swing shift supervisor Bill Hendricks, a former sheet metal worker, listened to floor workers, a rare opportunity for innovation in a rigid hierarchy. On February 11, Frank caught Hendricks during the 8 p.m. shift change and showed him his sketch. Hendricks studied it carefully, then said something Frank hadn't expected: "This violates every structural loading principle Boeing uses." "You know that, right?" Frank nodded, aware, or at least suspecting, the risks. Hendricks continued, explaining that the parallel rivet pattern wasn't arbitrary, it followed predictable stress lines along the wing, ensuring fasteners were densest where stress was highest, a principle rooted in Theodore von Karman's work at Caltech in the 1920s. A fully loaded B-17 wing experienced enormous bending stress in flight, and the parallel pattern perfectly distributed these forces. Frank's clusters, dense around structural ribs and following access convenience rather than stress lines, seemed gibberish from an engineering perspective. Under sustained combat, microfractures could propagate and the wing could fail, endangering lives. Hendricks shouted over pneumatic guns, acknowledging these risks, then asked a question that changed everything: had von Karman considered assembly efficiency? Frank looked confused. Frank returned to his rivet gun, expecting nothing. Rather than going to the head engineer, Hendricks approached Donald Douglas, assistant production manager and desperate to meet quotas. On February 18, Douglas dismissed the sketch as garbage until Hendricks presented 6 weeks of assembly time logs showing every wing had taken 19 to 22 hours, no crew had figured out a faster method. The bottleneck was structural, built into the process. Douglas understood that Boeing was weeks from losing the B-17 contract to consolidate it if production didn't dramatically improve. Risking protocols, he authorized a secret test for graveyard shift on February 21, using a damaged wing section. Frank and 4 experienced riveters volunteered, and he color-coded the blueprint to allow simultaneous work without interference. At midnight, the test began. Traditional sequential riveting gave way to controlled chaos, one worker inside the spar, another under the trailing edge, a third topside, all following clusters instead of rows. Douglas timed the operation, amazed as the wing reached 45% completion in just 2 hours, nearly double expected progress. Riveters weren't waiting, hoses weren't tangling, heat was distributed, and aluminum expansion reduced. At 2:21 a.m., 127 minutes after starting, the final rivet went in. Douglas inspected 30 rivets himself, then called in quality inspector Jimmy Chen, who ran his full protocol and found the wing virtually flawless, better than any wing he'd inspected in years, with a defect rate less than 1/10 normal. Still, structural engineering concerns remained. At 3:30 a.m., Douglas made another unauthorized decision, calling the night crew at Boeing's structural test facility to prepare an emergency stress test. They mounted the wing by 4:15 a.m., and the hydraulic press applied load simulating flight stresses. At 1G, 3G, and 6G, the wing flexed normally. At the 6.2G qualification threshold, it held perfectly. At 7G, still sound. At 8G, some strain appeared near the wing root as expected, but no rivets failed. At 8.4G, the test was halted, not due to wing failure, but out of fear of damaging the equipment. The wing returned to neutral with no permanent deformation, validating Frank's revolutionary approach. The wing showed zero permanent deformation. A properly designed wing stressed to 8.4G should have displayed some microscopic set, but this one behaved as if it had only seen 5G. Jimmy Chen ran his inspection protocol again, checking every rivet under maximum load. None had loosened or slipped. Somehow, the wing was stronger than those built to the standard pattern. Douglas, standing there at 5:47 a.m., tried to comprehend what he was witnessing. Frank's clusters had coincidentally reinforced the wing's natural load paths by concentrating rivets around the primary structural ribs, while radiating connections channeled stress away from weaker areas. It wasn't random, it was organic, aligning with the actual flow of forces rather than theoretical expectations. By 6 a.m., Douglas realized he needed someone who could authorize full implementation, bypassing Eccles, who would reject it outright. He woke James Murray, Boeing's vice president of operations, at home. Murray arrived at 7:15 a.m. in weekend clothes and demanded to see all data, test results, inspection reports, time logs. Douglas, hands shaking, explained what they'd done without authorization. Murray's face remained unreadable, then asked the crucial question, could 200 riveters be trained on the pattern by Monday? Douglas hadn't considered scaling, but Murray immediately calculated that if one wing dropped from 20 hours to 2, all 42 stations could increase output tenfold without adding workers. Wing assembly was the bottleneck, fix it and the line would flow. Over objections from Eccles, engineering, and legal, Murray ordered Frank's rivet pattern implemented across all lines effective February 25, 1942. He gave Frank a $40 weekly raise and the title of production method specialist, promoted Hendricks to senior supervisor, and assured Douglas his job was secure. The results were staggering. March 1942 saw 47 B-17s delivered, April, 91, June, 186. When all 42 stations fully adopted Frank's pattern in July, production soared to 284, then 319 in August, and 362 in September, more than the entire 1941 annual output. The impact on the air war was immediate. By October, the 8th Air Force flew its first 100-bomber mission against Lille, France. German defenses, built to counter 20 to 30 bombers, were overwhelmed, facing overlapping fields of fire the Luftwaffe dubbed the Wall of Lead. Losses for German pilots mounted while American bombers pressed on. By January 1943, missions involved 300 bombers, by summer, 500. Each represented 2 hours of riveting instead of 20, carrying 4,000 pounds of bombs deeper into Germany than Hitler had anticipated. The Schweinfurt-Regensburg raids in August 1943, crippling German ball bearing production, required 376 B-17s, an impossible number without Frank's pattern. The strategic bombing campaign, drawing German fighters from the Eastern Front and forcing unsustainable attrition, relied on Boeing flooding the skies. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had adopted variants of the pattern, producing 512 heavy bombers in a single month. German factories churned out 1,000 fighters monthly, but it was futile. You can't win an air war when bombers arrive faster than you can shoot them down. Frank Szymanski never gained fame. He received a War Production Board commendation in July 1943, hung in his daughter's bedroom until 1959. Boeing kept him on with a raise and title, but after the war, production method specialist roles were quietly eliminated during the 1946 workforce reduction. Frank returned to Detroit, worked at Ford for 23 years, and died in 1971, never knowing that his rivet pattern had revolutionized aircraft manufacturing. It didn't happen overnight or obviously, but it changed everything. The principle Frank stumbled onto in 1942 eventually became standard practice. By 1947, when Boeing began designing the B-47 Stratojet, their first swept-wing jet bomber, engineers no longer started with theoretical rivet patterns, they consulted assembly line workers about access points and workflow. The B-47's wings employed a pattern that looked chaotic on paper but allowed 6 workers to rivet simultaneously in 3 hours. Nobody called it the Szymanski method, and nobody knew who Frank Szymanski was. They just recognized that aligning rivet patterns with practical assembly realities, rather than purely structural theory, produced faster, stronger aircraft. Douglas Aircraft applied the same approach to the DC-8 in the late 1950s, Lockheed used it for the C-130 Hercules, and Boeing included assembly line supervisors in initial design reviews for the 707, employing cluster riveting, the same pattern Frank had pioneered. This cut fuselage assembly time by 60% compared to the Stratocruiser it replaced. The real legacy, however, was broader. The principle now called design for manufacturability, DFM, teaches engineers that a design's elegance is measured not only by performance but also by how efficiently it can be built. Textbooks at MIT, Caltech, and other aerospace programs highlight B-17 wing riveting as an example, showing how a theoretically optimal pattern proved inferior to a practically optimal one, and how reducing assembly time improved quality rather than degrading it. Most students never learn Frank's name. They learn about Boeing's production methodology development program as if it were a committee decision. Modern aircraft, like the Boeing 787, take this concept even further, using computer-generated fastener patterns optimized for robotic installation, accounting for loads, access, thermal expansion, and dozens of other variables simultaneously. Frank had done the same in 1942 with only a pencil and a time card, relying on pattern recognition from observing thousands of rivets and noting what slowed the workflow. He wasn't smarter or better educated than Boeing engineers, nor did he understand von Karman's stress equations, but he knew how assembly actually worked, how fatigue and tangled hoses caused delays, how theoretical perfection executed poorly produced worse results than theoretical imperfection executed flawlessly. Both types of knowledge, calculating stress and knowing how to build, are essential, yet only one was initially valued. The aerospace industry eventually realized this, creating integrated product teams where machinists and assemblers collaborate with engineers from day one.